Okay, so let us start with the 11th question of third chapter. And first let's analyze the question. The question says that we have to show that any component of momentum operator, okay, of a particle is compatible with the kinetic energy operator. So first we have to fix what is the momentum operator. So the momentum operator is the sum of, if we go with the Cartesian coordinates, then the moment operator is the sum of three components, okay, and the kinetic energy operator kinetic energy operator is one by 2m px square py square pz square. Okay, now we are asked to show that for any component of moment operator. So let's say we take px for, say, it's a random choice, okay, and we have to see if that's compatible with the kinetic energy operator. And that means in mathematical terms we have to show that px and t, commutator of px and t, is equals to 0. Okay, now this solution is px cap. Now substitute the value of this t over here. So it's 1 by 2m px square plus py square plus pz square. Okay, now we will separate these three, px square by 2m plus px py square by 2m pz pz square by 2m. Now from referring an equation from chapter 2, that is equation number, just a second, from chapter 2, referring to equation number 2.323. Please go and look up to equation 2.323 for further simplification of this three terms. Now we are having 1 by 2m px square plus 1 by 2m px py square by 2m px pz square. Now one of the identity that we know, if a and b commute, then a cap and some function of b cap also commutes. Also a cap and some function of that same number of that same operator also commutes. Okay, applying this to over here and this over here and here. Okay, so f of py is nothing but py square and f of pz is pz square. Okay, so b cap was py and f of b was py square. So now referring to equation 2.323, we can see that px and py commutes to 0. Okay, so we can say that px and py square commutes. Similarly, we can say that for px and pz square. So finally, we can reduce these two terms to 0. Okay, and now using this identity, we have px and px square, which will be reduced to 0, which implies this also reduced to 0. Therefore, we are left with px and kinetic energy operator are compatible. So any component of the momentum operator is compatible with the kinetic energy operator. So we finally at the result. Okay, so we are done with the first question. Now let's move on to the second one. So the second question asks us to show that the momentum operator is compatible with the Hamiltonian operator if the potential operator is constant in space. Okay, so let me put that in the mathematical view. So we have to show that P cap and H cap equals to 0 if V of R bar equals to V. Now the important thing here to note is that what does this mean by V R bar and V? Okay, so let me take more general potential operator. So let's see my potential as dependent on position and time, but due to given condition at present my potential is only dependent on time. It is independent of the space. Okay, so constant in space coordinates means it is independent, it doesn't depend on where your coordinates are. Alright, so this is what we have got till now. Now, what is the momentum operator? So momentum operator is in the position representation. I can write my momentum operator as IH cut into gradient and my Hamiltonian as minus H cut square by 2m into delta square plus Vt. Okay, or in other words, I can also write this as P cap into P square by 2m plus V of t. So now separating these terms, I have P square by 2m plus P V of t. Okay, now one thing that we have over here is from the previous slide, using this equation, this particular equation over here. Okay, so we have a commutator of a into some function of a that commutes to 0. So our function over here is p and its function p square. So this will obviously reduce to 0. Now we have to see how the other commutator will go. So minus IH cut into gradient of v of t. Okay. Now let's expand this commutator with some test function psi. So minus IH cut gradient into v of t into psi equals to minus IH cut gradient v of t. The psi is dependent on some position r and t minus v of t minus IH cut gradient of psi r t. Now this potential is independent of space and this gradient is taken over the space coordinates, so this potential can be taken out. Okay, so we are having minus IH cut v of t gradient of psi r bar comma t plus v of t IH cut gradient psi r bar comma t. So these two terms get cancelled, which implies my p cap and v of t is equals to 0, so that they are compatible. Substituting this result into over here, so what finally we have is p cap into Hamiltonian is compatible if v r bar comma t, our generalized potential, depends only on time, or rather in other words we can say that potential operator is constant in space. So that is it for the video, or that is it for the particular question. I hope you find this helpful. Thank you for watching the video.